Hello everyone and welcome to lesson 8.1. This is the introduction to exponential and logarithmic functions. As it kind of says typed right here, in Algebra 1 you discuss exponential functions, but you don't do a ton with them. You learn what the graphs of them look like, how to maybe identify the features of the graph, and maybe you do a few word problems that exponential functions kind of help model. Yeah, so you write the equations for it. But your abilities with exponential functions are a little limited in Algebra 1 because you can't really solve things. There's a few you could, but even that would be a little tricky. And in order to really solve most exponential equations, you're probably going to need something called a logarithm. So it says right there, in this lesson, we're going to introduce logarithmic functions. So what is a log? How does that work? You know, all that good stuff. So these two functions go hand in hand, and they're the last two functions of study in this course. You know, we've covered all the other parent functions. These are the last two. There are, of course, more units after this, but they're not really on functions like this. So anyway, let's get started here with a few Algebra 1 reminders. Yeah, what do we remember about exponential functions? Well, basic exponential functions, see the keyword basic here, right? Because you could have more complicated ones. A basic one is written as y equals a times b to the x. Yeah? What are these letters? What does this mean? Well, you know, y is the function. X, which is the variable, is in the exponent. So different from a polynomial. You see, the difference being x squared is a quadratic, right? It makes this U shape like so. But if I kind of switch those and I say 2 to the power of x, right? 2 is what I call the base, and then the variable is actually in the exponent. And that does not create a parabola. It actually creates something that looks like this, which you might recognize from Algebra 1. And so what are these numbers? What do these constants mean? Well, a is just a coefficient on the exponential expression. So something to note, a is a real number, but a is not 0. Reason being, if you said y equals 0 times b to the x, that would just be a constant 0 function, which doesn't change, right? And so that doesn't really meet our criteria for what we mean by exponential. If the function is left purely in this form with no other transformations, no shift left, no shift right, then you can say that a is the y-intercept. You might say, well, how do we know that? Well, y-intercepts happen when x is 0, right? Something we've talked about all year. So in this equation, if I make x 0, then that's b to the 0, and any number to the power of 0 is 1. So that would just get you a. Meaning, if you plug in 0 for x, you get a as the result. That's the y-intercept. Yeah? Then, something about b. So b is also a real number, but there are two conditions on b. First of all, b is not 1. Reason being, 1 to the x. You know, you consider 1 to the 1, 1 squared, 1 cubed, 1 to the 4th, and so forth. All of those results are going to equal 1, which is constant and doesn't change. So we were not ever really going to use a base of 1 because it really, again, wouldn't classify something doing exponential change. We're also going to put the stipulation that b is a positive number. You see, b must be more than 0. The base that we use, by the way, b is called the base, all right? The base that you use needs to be a positive number. Now, it can be a fraction or an irrational number, and that's fine, but it needs to be positive. Here's why. Suppose you had negative 2 to the x. Well, there's two things about this. One, it's not a continuous function, and the behavior flip-flops for every integer. You know, what? What is he talking about? Well, negative 2 to the first power is negative 2. Negative 2 squared is positive 4. negative 3 squared, sorry, negative 2 cubed is negative 8. Negative 2 to the fourth is positive 16. And so you kind of have this flip-flop alternating nature. You know, you're going down here, then here, then here, then here, and so forth. And it's not smoothly connected through those points. And we know that because, well, what's a number between 0 and 1? Maybe a half. So negative 2 to the half. What does that mean? Well, in Unit 6, we recall that a power of a half is like a square root. And the square root of negative 2 is what we call imaginary. So this wouldn't even be graphable on the real plane, so we're not going to do that. Yeah. So that's just a few things. That's not something you're really super tested on, but, you know, it's important to note. Yeah. You're not going to use a base of 1, and you're always going to use a positive number as the base. Okay. Two things that you should know about the base b is if b is more than 1, right? So this could be 2 to the x, 3 to the x, 4 to the x. It could also be like 1.5 to the x or 5/4 to the x. All of these numbers, all of these bases are more than 1. If this happens, you see b is called the growth factor of your exponential, which is to say that is what you're multiplying by every time. You see, if you do 2 to the x, 2, 4, 8, 16, you're doubling this, right? So if it's more than 1, you're multiplying by a quantity that's going to increase your y values, right? That means this would be called exponential growth. It's going to grow or increase, okay? So we're going to use this word a lot, growth. It's a growth function, right? And it looks like whoop, something like this, which is something you're familiar with. The other type of base you could have is one that is less than 1. Now, I do, again, say that it's more than 0 because we don't want it to be positive, but this idea being a half to the x or like 0.35 to the x, right? These bases are less than 1, and so these cause a decrease in the function. So they're going to come down like this. They're not growing. They are what we call decaying. It's called exponential decay. All right? And that's the vocabulary there. You know, we spend some time talking about that because it's important. You've got to have the language behind how you talk about these things. So just make sure you understand this because there's going to be some homework questions. For example, 4 times 3 halves to the x. And it's going to ask you, is that a growth function or decay function? And you say, oh, I know that it's a growth function because 3 over 2 is 1.5, which is more than 1. Therefore, it classifies as growth. Yeah? So, you know, just something to look out there. Okay. Let's move on. We're going to do a few graphs of these. Again, just some good review of exponential functions. And talking about the parent function, y equals b to the x. No a coefficient, just a base and an exponent. That is what an exponential is at its core. Yeah? Well, you can do 2 to the x, you can do 3 to the x, you can do 10 to the x, you can do 5 to the x, right? You get to choose the base, right? Or maybe it'll be given to us. All of these are different functions because they grow at different rates. See, 2 to the x doubles. So 2, 4, 8, 16. 3 triples. So it's like 3, 9, 27, 81, and so forth, right? 10, 100, 1,000. So they all grow at totally different rates. That means they're all different functions. So every one of these is a different kind of parent function, but they're all exponential, okay? The graph of 2 to the x, we're just going to quickly generate that. -2, -1, 0, 1, 2 for our x values. Maybe put a 3 in there as well. We've pretty much already done this one in what I've been saying. 2 to the 0 power is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8, right? That's that doubling pattern that we're seeing. Times 2, times 2, times 2. Now, going backwards, it's cutting in half. 8 cut in half is 4. 4 cut in half is 2, so forth. If you take 1 and cut it in half, it's a half. And you take a half, cut it in half, it's a quarter. And this makes sense because if you had 2 to the negative 2, what's a negative exponent again? So, well, a negative exponent is you'd say 1 over 2 squared. Or in other words, 1 over 4. That's why that we have that 1/4 there, okay? It is important, quite important, I should say, that you understand what negative exponents do. We've already talked about it, but, it's been, you had spring break. Yeah, you were chilling, right? This is you laying in bed, and you're happy. Well, it looks like you're crying, but actually you're happy. You've got a little party hat, and you're watching television. Okay, TVs don't have antennas anymore, but whatever, right? Okay, all right. Anyway, you've come back from spring break. You're having a great time learning about math again. Yes. So let's graph this, right? Plot these points, 0, 1, 1, 2, 2, 4, 3, 8. And going the other direction, -1, half, -2, 1/4. And those are going to keep on going down and down. And something to keep in mind is if you keep cutting those fractions in half, a 4th cut in half is an 8th, cut in half is a 16th, cut in half is a 32nd, right? These are going to keep decreasing and they become really large fractions like 1 over 2048, right? Which is really small, but not quite 0, right? And so what's going to happen here is we're going to get an asymptote at 0. You might recall this from Algebra 1. Okay? And so I have this nice dotted line for my horizontal asymptote, and I'm going to smoothly, as much as I can on this iPad, connect the points like that. Okay? And that is my basic parent function. Good to know the basic features because we do transformations on those. Now, analyzing the basic characteristics, your x-intercept, well, you don't have one because you don't touch the horizontal asymptote. The y-intercept, we found that from the table. You always find the y-intercept by plugging in 0 for x. And the horizontal asymptote is the equation y equals 0. Looking at the graph, the domain is plotted for all real numbers. So we'll just go ahead and put a double R there. And the range is limited, actually. You see the range, there is no function within the negatives. Everything is from 0 and up. So 2 ways to note this. You could say y is more than 0, or you could say parentheses 0 to infinity for interval notation. Keep in mind, this does not say equal to, and it does not say bracket, right? It's specifically strictly greater than and parenthesis. This is because we don't touch the asymptote, okay? All right. That's the parent function, and then you move on to example 2, and this is the point of the class where I really hand it to you, the student, to kind of play around with this and get some points, right? Now, common theme throughout the class, and when you're generating graphs, how do you plot graphs? Well, you just plug in stuff, right? And sometimes you plug in a number and it doesn't really look pretty or it doesn't do what we're hoping to do, so pick a different number, yeah? If you'd like to try this example, go ahead, do so, but we're just going to pick numbers, and I'm just going to pick good ones, yeah? If I look at this function, right, there's a few things going on here. The 3 is like your A, the 2 is like your B, and then there's that power x, right? But there's a few other things going on here because the exponent is actually x minus 1, and then there's a constant minus 5 subtracted from the expression, yeah? If you recall your function transformations, these do all the same transformations you're already familiar with. Suppose it was like a square root function, right? That would say 3 square root x minus 1 minus 5. And you would say, oh, yeah, that seems familiar. 3 does a vertical stretch, right? x minus 1 moves right 1. Okay, I'm I'm losing it there. That moves right 1, and then minus 5 moves down 5, right? Okay, well, all of that is the same for this exponential function. So it's a vertical stretch, moves right 1, and not up, down 5. Okay? Sometimes what students get confused here is they say, well, what's the 2 do? Does it do like horizontal compression or something? And it's like, well, no, the 2 is what the parent function is because it's 2 to the x. You know, it could have been 3 to the x or it could have been 5 to the x, but the function in question is 2 to the x. Sometimes I see that students say, what is the 2 doing? It's not doing anything. It's just that's the function, okay? The 3 stretches it, the minus 1 moves it right, the minus 5 moves it down. Okay, knowing that, I'm going to just start plugging in points now, and we'll just go ahead and do that. Let's say, let's plug in 1. So if I plug in 1, then I get 3 times 2 to the 1 minus 1 minus 5. Okay, well, 1 minus 1 is 0, so that's 3 times 2 to the 0. Of course, 2 to the power of 0 is 1, so that's just 3 times 1 minus 5 is negative 2. Boom, I get this, okay? And you're just going to replicate this process, right? You plugged in 1, you got negative 2. Let's try 2. Then 2 minus 1 is a 1, and 3 times 2 is 6, right? So this is now 6 minus 5, which is now 1. Okay, let's do one more. Let's plug in 3. Happy days. 3 times 2 to the 3 minus 1 is 2. And then keep in mind of your order of operations here. Yeah, sometimes students mess this up. Mistake, okay? Mistake is to say that it's 3 times 2 squared, so that it's 6 squared. Okay, you don't do that. You say, I'm going to square 2 first, 3 times 4, and then minus 5. So that's 12 minus 5, which is 7. So you plug in 3, and you get out 7. Okay, so just be careful with that. And let's plot those points. 1 comma negative 2, 2 comma 1, and 3 comma 7. Beautiful. Fantastic points there. And you can find some more points, right? We might like to find the y-intercept, which can be found by plugging in 0. So if I plug in 0, you know, I would have 3 times 2 to the negative 1 minus 5, okay? Well, what's a negative power do again? It makes a fraction. So 2 to the negative 1 becomes a half, like so. So now it's 3 times a half, which is 1.5. Then subtracted by 5 is negative 3.5. So I have the point 0 comma negative 3.5. That's like roughly right there. Okay, trying to kind of ballpark that as much as I can. Yeah, and so we found the y-intercept. And you could try and find more points, but this is pretty good. Also, I think I messed up that point. That point should be right there. Okay, fixed it. So the y-intercept, we have x-intercept. We'll get to that in a second. Where's the asymptote, right? Some students say, oh, I think the asymptote's at 4, right? Negative 4. Because it kind of looks like it's getting close to negative 4 and going to do this. And I'd say, well, maybe, but how do you know, right? How do you really know where the asymptote is? 2 ways you could maybe do this. The first way is to keep plugging in numbers to see what you're really approaching. So, for example, you could plug in negative 1, and then that would get you 3 times 2 to the negative 2, then minus 5. So that's essentially 3 times 1/4 minus 5. Or in other words, 0.75 minus 5, right? Which is negative 4.25. So actually at negative 1, it goes down to negative 4.25. So it's actually not at negative 4 because it just passed negative 4. How many of these should you do, though, till you really find out where it's approaching? Well, I wouldn't do a ton of them, actually. What I would do instead is look at our transformations. right? Remember that the parent function for 2 to the x, it had a horizontal asymptote at 0, right? It was just right here, flatlined at 0. Well, we have shifted this graph down 5. That means the new horizontal asymptote is at -5 right here. All right? And so then that makes our exponential curve. Whoa. Okay. Let me redo that just one more really quickly. Woo. Okay, that's not really better, but whatever. I'm not going to make that better. I'm sorry. Okay, maybe I will. Whee. Okay, that's a little bit better. And there's my function, right? So my asymptote is at y equals -5. And seeing the graph, the domain is all real numbers. The range, its bottom near the asymptote is at -5, but it extends upwards to infinity. Okay, then the question is, what's the x-intercept, huh? What's that? The x-intercept. Well, how do you find that? I say, well, look at this. I say, No, make a, Whoa, okay, got silly there. I was trying to be inquisitive, but this just looks silly. Okay, let's make this. No. That's better. That's better. I like that. Right? Where's the x-intercept? Well, it looks like it's about right there. What is that? Like roughly 1.5, maybe? I don't know. But it kind of looks close to 2. Maybe it's more like 1.6 or 1.7, right? But that's really hard to tell. Maybe it's a nice fraction number, like, I don't know, 7/4, maybe. But how would I know that, right? Okay, so, well, how do you find x-intercepts? Well, to find a y-intercept, you set x equal to 0. To find an x-intercept, you set y equal to 0. So you say 3 times 2 to the x minus 1 minus 5 set equal to 0. Then this is an exponential equation to solve for the x-intercept. So how would I do that? Well, I would add 5, and then I would divide by 3 to get this exponential expression alone. And then, well, 2 to what power is 5/3? I don't know. I don't know what 2 to... No, there is... I don't know what power. I guess 1.6 something, right? Maybe 1.7 something. But that's not, when I say powers of 2, I think 2 and 4 and 8 and 16. I don't think about 5/3, right? So we're just going to say, I don't know. I don't know. I don't know. Like roughly 1.7 maybe? Question mark? I don't know. And if you say that on your test, you will lose points because you need to find this. No, I'm kidding. How would you find this? Well, right now, we're too limited. We don't have enough knowledge to actually finish this problem. Because what would you do? 2 to the x minus 1 equals 5/3. Here are some student strategies I've seen. Divide both sides by 2. That doesn't do what you think it does. Because students think, oh, if you divide by 2, then it's just x minus 1 is 5/6. No, that's not how exponents work. So you can't do that. And then some students had a really great idea of saying, ooh, what if you took the x minus 1 root of 2 to the x minus 1? And that got you x minus 1 root 5/3, right? That way you would have 2 here. I said, well... Did that really help, though? Did that get rid of the x and isolate it in any way? Not really, right? So, as it turns out, we can't progress. We can't find the x-intercept here. And that is why we learn about something called logarithms. Yeah? So, logs are going to help us deal with these instances where you have an equation that you're trying to solve, but you can't really reason it out. And so logarithms are a device invented to help work with exponentials in this way. Okay. For now, we're going to leave it as I don't know, it's like 1.7. Though eventually you're going to learn how to do this and you'll be prepared. Yeah? Okay. So we move to the next one here. Okay. Should I split this? I think I'm going to split this into two parts. I want to wrap up the last piece here talking about e, and then I want to talk about the inverse of exponential functions. And then, no, I will wrap up the video here with talking about e, all right? And this is just to set the stage for the next for the following days that we study. So there is a number, and its name is e. And you said, Mr. Spake, you are so silly. E is a letter, not a number. And I say, okay, look, it represents a very special number, all right? You know pi. You're familiar with pi. Pi is, roughly an estimate, 3.14. It isn't 3.14, it's approximately 3.14 because pi is what you call an irrational number, right? It's this very specific special number that pops up because of circles, because pi is the ratio of a circle's circumference to its diameter. And so anytime you're working with circles, pi pops up, right? Well, e is a new number that you may or may not have seen before. And so I'm going to talk about that just a little bit here. E is also a number, much like pi is. It's approximately 2.718, roughly. If you want to round that liberally to 2.7, that might service, your needs usually. But it's about that, okay? But like pi, it's an irrational number that continues on and on and on forever. But what is this number, and where does it really come from, and why are we going to be talking about it? So, first of all, E was discovered, I'm going to come right here. E was first discovered by a mathematician called Jacob Bernoulli. Bernoulli was he, I guess that's Italian, maybe French. I'm trying to remember, though it's escaping me at the moment. Bernoulli was a mathematician who put a lot of progress towards statistics, yeah? So there's some like Bernoulli tests and stuff like this that if you take AP stats, you're going to see this name pop up, yeah? And he is the one who first discovered this interesting special number, 2.718, and it came from compound interest. You may know what that is, maybe you don't. To give a brief description, interest, I'm hoping you're familiar. Interest, you take out a loan, right? I say, okay, you loan me out $1,000, and then I charge you a 2% monthly interest. That means for every month you don't pay me, I'm going to charge 2% on that 1,000, and then you're going to pay me that in addition to whatever you owe me, right? And that's the idea of interest. Compound interest means it's interest that's accumulated or compounded in such a way. We're going to get into the specifics of that in lesson 8.4, but just so you know, this number pops up from a sort of financial perspective, yeah? Bernoulli found this number through, working through compound interest and seeing where these numbers were kind of behaving. Originally, it was denoted B for Bernoulli. But the thing is, this guy comes along, and his name's Leonhard Euler. All right, notice how that's spelled, Euler, right? You pronounce this Euler. Leonhard Euler is like a top 10 mathematician, all right? He is a huge name in mathematics. His contributions to all sorts of fields are incredibly notable, and we use so much of it still today, and especially in how we teach and with number theory. And so this number E, Bernoulli discovered it, but Euler did more with it. Yeah, Bernoulli found it, made note of it, maybe did a few things, but Euler really took it and showed the world why you must love E. We love E, just like we love pi. And we love this kind of pie. Yes. But we love E because it has many, many occurrences where it pops up in math that you really wouldn't expect. And it's an extremely useful function on its own. So this is stuff we're going to be getting into throughout the unit, but that's kind of a gist of what E is. Though there's a few more comments I want to make. Pi and E are known as transcendental numbers, which is actually different from irrational. What is a transcendental number? It's, well, you know how we studied polynomials, such as 4x squared minus 7? Okay. When you find the root of a polynomial, you set that equal to 0 and solve for x. You can get all sorts of numbers. You can get irrational numbers, you can get rational numbers, you can get whole numbers, right? You get all sorts of answers. You can get imaginary numbers, right? But what is a transcendental number? It is a number that is not, it could never be a root of an integer polynomial. So those basic polynomials we've studied, you would never get pi as an answer, and E, you would never get that as an answer either, all right? As I was mentioning, E as a function is very powerful, very loved. You know, we have 2 to the x, we have 10 to the x. E to the x, this is, I'm going to call him the GOAT. Yes, the greatest of all time. Yeah, E to the x is one of the most powerful functions in all of calculus. And there's a reason for it. It has to do with what's called a derivative. But I don't want to spoil that today. Do you see my joke? Spoilers. You see, because Euler, and then you put a little here, and then it's spoilers. Okay, so I'm not going to spoil this right now, because I'm hoping that you will take calculus to see why this function is so awesome, to see why this function is the GOAT, yeah? Because e to the x is one of the easiest functions to work with in calculus. We love it, all right? And you just take my word for now. Also, since it comes from a financial context, you can usually use it for various types of interest. In particular, student loan debt can be very closely approximated with the equation PE to the RT, where P is how much money you take out, R is your interest rate, and T is the time that passes. Yeah? So this formula can be used to really accurately determine how much you're going to owe every month when you make student loan payments, which is kind of cool. You can actually use that in your real world life. And then lastly here, just a little fun tidbit. At the time of recording this video, in 2020, there was a world record set for approximating E up to 31 trillion digits. Yeah, that's 31 trillion right there. It's not just 31 trillion, given by David Crissell here. It's 31 trillion in terms of pi many digits. See, look, 3.141592665. Those are the digits of pi, right? So this is a funny little thing he wanted to do by setting the world record with a pi number of digits for E, since these are the two most well-known transcendental numbers. Sadly, Crystal's joke was his little tongue-in-cheek thing here was actually recently beaten in 2024 by Jordan Renew. I think that's how you say that. Maybe Raynow. I don't know. Who approximated E to 35 trillion digits. Okay. So yeah, just some interesting things there. And that is about that for E. It's just an interesting number that's going to come up. So, okay. I think I said I was going to split this video into 2 parts. The next part is going to cover logarithms. Okay, so this was just an introduction and review of exponentials. In the second part, we're going to talk about logarithms. What is the definition of a logarithm? Where did they come from? How do we use it? And what do their graphs look like? Okay, so thanks for watching this one, and I'll see you in the next part.